Okay, so I'll be taking you, I'll be starting from question 4, and I hope I can be much more concise so that you can understand what is going on. Okay, now question 4 reads thus: propose a simple two-step mechanism for 2 moles of ozone giving you 3 moles of oxygen gas, where the first step is slow and unimolecular and the second step is fast and bimolecular. Derive the rate law using the steady state approximation for the intermediate. Now, so the question is divided into 2 parts. So you have to propose the mechanism, right? And then you have to derive the rate law using the steady state approximation. Okay, for the intermediate. So take note of that. So the first step, proposing the two-step mechanism, right? So this is how you approach it. So the first step there is unimolecular and it is slow. That is, it is the rate determining step, as I taught you um, during my class. So what you need to do is, first step will be O3, K1 giving you O2 plus O. So then the second step will be the O combining with 1 molecule of ozone to give you 2 moles of oxygen gas. So that's K2. So this is a fast step. The first one is a slow and rate determining step. So that is the first section. So you've answered the first section. The second one it's much more tasking, because there you have to use steady state approximation, for the intermediate, and then you have to put it into the main rate equation for the product before you get your answer. So let's first of all get the steady state approximation going. Now, to do the steady state approximation, you need to first of all take it as, okay, DO. So remember what is your intermediate here? Your intermediate is oxygen, right? Oxygen is formed here and it is used up here. Okay, formed in the first step, used up in the second step. So that is your intermediate. So to write a steady state approximation for the intermediate, you do a DO, right? That's intermediate DO dt, which is what you can see here. DO dt for this first step will be DO dt is equals to K1 O3, right? For the second step, DO dt will be 2K2 O3 and O, which is what you have here. Okay, so that's step 1 and step 2. Now remember, like I did in class, your steady state approximation, you during that is the major step where you equate it to 0. Okay, so changing the concentration of the intermediate over time will be equal to 0. And so what you get here is K1 O3 for the first step, then with the minus K2 O3 for the second step will be equal to 0, right? So bearing this in mind, you can simply factor out O3. When you factor out O3, you move it to the other side, everything becomes 0. So what you are left with is K1 is equal to K1 minus K2O, right? And from that you get K1 is equals to K2O, and then K1 over K2 is equals to O. So you can work this out on your own to make O the subject of formula. And when you do that, you get this. So K1 over K2 is equals to O. Okay. Now that is the equation for your intermediate. So this equation you are going to put it into the rate equation for the product, which is what we are about to do next. So for the product is O2, right? So you do the rate equation for the product. So this is for the first step, which is K1O3 plus 2K2O3. Okay. Now with this, we have O here, right, in the rate equation for the product. So you put in what you have as O into this equation, and then you get this, right? So K2 will cancel out K2, and then you get 3K1O3. Now all you need to do next is just to push the 3 to the other side, okay, so that you have 1 over 3 the O2 dt is equals to K1O3. So K1O3 is your answer. So you can stop here. That is for that. So now the next question under week 3, we have draw the classic explosion peninsula diagram for the H2O2 system. For each limit, briefly explain the competition between the chain branching and chain termination that defines the boundary. So first thing, you draw the diagram, okay, and then you explain the competition between chain branching and chain termination. Now this is what, so practice so that you can reproduce this. So you need to practice, sketch it again and again, and I'm sure you'll be fine. So first of all, you have the y-axis here, which is reaction rate. Then the x-axis, you have pressure, right? So you might not bother about the values here. All I want you to know is how this proceeds. Okay, so start with the first explosion limit. So and then you move on to the chain branching. Okay, so chain branching dominates here, and then you can have a chain termination, which is the third explosion limit in some cases, or you can move on to form the second explosion limit by further chain branching, and then you end it with a third explosion limit. So you have the first curve, and then you have some minor ones, two smaller ones inside. So that's all you need to do, okay, to answer that first part. Then the second part, which talks about the competition, so then threefold. So you have the first explosion limit, low pressure. So at this point, so there's competition between chain branching and wall termination. The second explosion limit, which is the intermediate pressure, you have a competition between chain branching and gas phase termination. And then the third explosion limit, which is the high pressure, this is here you have reactivation, okay, reactivation occurring, reactivation of, in this case, of HO2 through the following reactions. So that's it for that question. The next question, draw the mechanism for H2 plus Br2, okay, giving 2 moles of HBr. So and then label initiation, propagation, and termination steps. Use Lewis structures, chemical formulas, and show electron movement with half arrows. Okay, so this is quite easy. So you have been given been given the equation already. H2 plus Br2 then gives 2 HBr. In initiation, you have Br, Pr, okay. HV here means that that's electromagnetic radiation, in this case light, so that means that it is initiated using light, okay, and then it breaks down to give 2 HBr. Please, you can discountenance or leave out this other 2Br, okay, just put 2Br dot, that's okay. Then here you have uh 2Br. I would prefer the second one, the one with the two dots, okay. So then you have the Br dot dot plus H plus, that's H, the 2H, so you have H and H, okay. So what you get here is this, there'll be a transfer of, that's why you have the electrons here. So for this to occur, okay, this H will become the more positive one relative to the other H, and that is why the electron moves. So you need to draw the arrow down there, so you can see the electron moving to this side, so it means it is this H that binds to the Br to give us HBr. While the electron moves here, this becomes electron rich, okay, and it forms a radical. So you can see a radical formed here. So this is propagation 1. Propagation 2, you can now have that H, okay, active energized H or unstable H reacting with Br2 to give HBr plus Br, okay, the radical, the bromide radical. So that's propagation 2. So take note of these two steps under propagation. Then for termination you have 3. So the H radical can combine with the bromide radical to give HBr. That's one termination step. Another termination step is Br radical, bromide radical with another bromide radical to give you Br2, or hydrogen radical with another to give H2. So these are 3 possible termination steps. So with that, you've answered this question. Now to the next one. What is a branching chain reaction? Give an example and explain why it can lead to explosions. So 1. Branching chain reaction. 2. Example. 3. Why it can lead to explosion. So 3 questions in one. So now what is it? So a branching chain reaction is a chemical process in which one reactive intermediate, that's a radical, so you can use radical or intermediate, produces more than one new radical in a single propagation step, okay. So this multiplication of chain carriers causes the number of active radicals and thus the reaction rate to increase exponentially with time. If you want to put it in your own words, you can simply say that a branching chain reaction is a chemical process in which a radical produces more than one new radical in a single propagation step, okay. And as a result of the multiplication, okay, or rapid increase in the number of active radicals, then the reaction rate increases exponentially over time, okay. So that is it. Now an example, a classic example is the reaction between hydrogen and oxygen. So that is a classic example. Then to the third part of the question, so it says why it can lead to explosion. Yes, so explosion happens, but let's start with the beginning. So we are using the example to answer the third part. So the third part, for you to get explosion, so no, you can leave this out for the your answer. Don't bother about this. You can leave this out. So I just need that. So why it leads to explosion? So the explosion occurs when the rate of chain branching exceeds the rate of chain termination. Okay, so remember chain branching, you're having one radical producing several radicals. Okay, as you can see up here. So here you see one radical producing two radicals, one radical producing two radicals in the first two steps. So that is what leads to an explosion. So an explosion means that you have generation of so many radicals. Okay, and so before you know it, you know, lots of heat is generated, and then if the heat is not quickly dissipated, okay, you have thermal, you have pressure buildup, and the pressure buildup leads to an explosion. So that's just it. So this is your answer. Okay, this is your answer for the third part. Okay, now move to the next question. The decomposition of ammonia to tungsten, so you are given the equation is zero order at high pressure. So given K is equals to 2.5 times 10 raised to power minus 4 mole per then meter square per second, and surface area is 1 meter square. Calculate the rate of uh, nitrogen gas production in mole per second. Okay, so this is quite an easy one. Now, all you need to do is just go straight to the solution, which is just this. Okay, that is your solution. So you talk about rate. Rate is equals to Ka, and Ka is equals to 1. So K is 1, right? So you can see surface area is 1. K is 1 times 2.5 times 10 raised to power minus 4, of course, which we know is same thing as 2.5 times 10 raised to power minus 4. So that's what you get here. Okay, now to answer the question, the rate we are looking for is not for ammonia, is for nitrogen gas. So, but remember that when you look at this equation, 2 moles of ammonia will produce 1 mole of what? Nitrogen gas. So that means the number of moles of nitrogen gas is half of that of what? Of ammonia. So that will also determine the rate in this case, since it's zero order. And so we can now say that uh, the rate of for nitrogen gas is half that of ammonia, and so you simply divide the rate for the ammonia by 2, and then you get your answer. Simple. Okay, next, this is another simple one. Draw the potential energy diagram for the uncatalyzed gas phase and catalyzed using platinum. Okay, so this is the reaction: carbon monoxide with oxygen to give you carbon dioxide. Now on the same axis, so you are doing it on the same diagram. Okay, so y-axis potential energy, x-axis reaction coordinate. Now you draw the first part. You have reactant here. Okay, this is your reactant, so you have your reactant here, and then you draw this. Okay, and then you get your product, which is CO2, right? So you put that there, and then you can move on to draw a second one, which is lower. You can see this one is lower. Okay, so this is the catalyzed, the lower one is the catalyzed part. Now then label EA catalyzed. So you start your arrow from here and you pull it down to please pull it down to where you have your reactant, please. So that is where you have your reactant. To then to the top of this, okay, to the top of this, let it be above the product, please. So it shouldn't be, it should be above the product. and then come down to where the reactants, the same line with the reactant. Now it indicates the likely rate determining step. So this is the rate determining step. So this is what you are going to do. Okay, so likely rate determining step. So it's where you have CO with combining with O. Okay, so you just circle it, and that's it. Okay, now for the Haber process catalyst, that's question 3. Fe with alumina and K2O promoters. So explain the role of each component. Okay, now we know what the Haber process is about. So that's N2 plus 3H2 gives 2 moles of ammonia. So it's an industrial process for synthesis of ammonia. And the catalyst we have here. Okay, now each component plays a distinct role. So what is the role of each one of these? Now, so that is what this is simply asking in that reaction. So these three are used. Okay, now iron is the active catalyst. So take note of it provides the active sites for adsorption and dissociation of N2 and H2. That is what I need. Now alumina, okay, is the structural promoter. So it disperses the ion particles and prevents their sintering growth. That sintering or growth at high operating temperatures. So next, so it just ensures that the ion particles are properly dispersed, so that they don't clump together and form something else at high temperature, okay, which is possible for ion particles. Now, potassium oxide is an electronic promoter. So it donates electrons to the ion surface, increasing its electron density. Simple. That's all I need for this. Now sketch a Langmuir adsorption isotherm. Okay, so you have theta versus P, given K is equals to 10 per atmosphere for carbon monoxide on palladium. Calculate the pressure for theta is equals to 0.5. Now this is simply it, nothing out of the ordinary. So this is what you need to draw. So there you have surface coverage, that's theta over pressure P, and then you start from 0 and then you drag it to 1. Just make sure it's a fine curve, it is neatly done. So that is all you need to do. Okay, now the second part of the question says calculate the pressure for theta is equals to 0.5. So all you need to do is, so you have been given, okay, so you have been given K. So K is 10 per atmosphere. Now this is the equation you're going to use. 0.5 is equals to 10p over, so that's for kp. So it's actually theta, that's the equation, is theta is equals to kp over 1 plus kp. So that's the equation. So that's why I've put in this. So 0.5 is equals to 10p over 1 plus 10p. And then you make p subject of the formula. Okay, when you do that, you get this. Okay, so then you get your answer. So try a hunt on that. Next question is, okay, similar here, very similar to what you have just done. Adsorption of a gas onto a solid surface follows the Langmuir isotherm at a pressure of 0.5 bar and fractional surface coverage, okay, is 0.25. Calculate the pressure required to achieve a fractional coverage of 0.75. So use the Langmuir. So you have been given the answer already, okay, based on the equation you are given here. So you have your answer. So all you need to do is just to input the values. Now find k from the first data point. So you are given, so your delta, your theta is 0.25, k, okay, and p, your p is 0.5. So it's you are looking for k now, k, and 1 plus k, then 0.5. So it's your k you are looking for. You have p and you have theta. So you just need to make your k subject of formula, and then you get your answer. Okay, so try it out and see whether this is what you get. Now you now want to calculate the pressure when it is, now I want to get the pressure, okay, when your theta is 0.75. So k is constant for in both conditions. So now you have changed your theta to 0.75. Your k, you have gotten it 0.0667, right? And then you want to get your p. So all you now need to do is to make your p the subject of formula, and you should get 4.5 bar. So also try it out to see whether you're actually going to get 4.5 bar. 6, you are looking at compare and contrast physisorption and chemisorption in terms of bond type, strength, temperature dependence, and role in catalysis. So you are comparing physisorption and chemisorption. So what are these? So I'll start with the with adsorption and absorption. I'm sure you've heard that before. So absorption is when the substance penetrates into the bulk of the material. It enters, like when you pour water onto your foam, okay, so the foam absorbs the water, ab, absorbs ab. Then but when you, let's say for instance you are coating a surface, just the surface, okay, you call that adsorption. Adsorption means that the substance you are applying stays on the surface. Whatever you are attaching stays on the surface. That is adsorption. Ad, adsorption. While absorption means that it penetrates the surface and enters into the bulk of the material. So that is the difference between absorption and adsorption. Now there are different types of adsorption, okay. So adsorption can be physisorption or chemisorption. So it is physisorption when it is physically attached, okay, so using physical forces, so or weak forces. But when you have strong chemical bonds, okay, attaching the substance to the surface, then you call it chemisorption. So bond type weak. Now to the question, we want to answer the question now. So the bond type for physisorption, they are weak van der Waals, okay, forces. For chemisorption, they are strong chemical bonds. The strength is low for physisorption, but the strength is high for chemisorption. Temperature dependence, so for physisorption it is usually exothermic, okay, while for chemisorption, so it is often activated. Now in catalysis, the role in catalysis, so physisorption brings the molecules close to the surface, okay, that is just the job of physisorption. But chemisorption actually activates the reactants by breaking and forming bonds. That's it. So that's how you compare the two. Now we're about to end this, so let's go to our, I think this should be the last week. So on under photochemistry, draw a labeled Jablonski diagram. So I include all of this: S not S1, T1 absorption, fluorescence, phosphorescence, IC. Use it to explain the major difference between fluorescence and phosphorescence and why phosphorescence is slower. Okay, now when you look consider this, you see that the S you have S naught, okay, or S0, that's the ground state. So when it absorbs light, okay, you can have what you call some of course you have excitation, okay, to S1, right? Excitation to S1 there. So that's via absorption. But fluorescence, for fluorescence it falls fast, that's why I say fluorescence fast, while for phosphorescence it goes through intersystem crossing before it comes back to ground state, that's phosphorescence. So what's the implication of this? This is the implication. The implication is I'm sure you'll have seen maybe your dollar note, okay? If you have held a dollar note, you notice that when you put a UV light, okay, when you put it under a UV light, some features will appear, right, under the dollar note to show whether it is authentic or fake. So what you're having there is fluorescence, okay, because it will show. But once you remove the light, what happens to that? The features on the dollar note, it will disappear. So that's fluorescence. So once you remove the source, it will disappear. But for phosphorescence is different. For phosphorescence, when you remove the source, it will still show for some time. Example, you can see some rosaries, for instance, the Catholic rosaries. Okay, when light goes off, what happens? It will glow for a long time before it finally what dims and it will stop glowing at all. So that's phosphorescence occurring. But nowadays you have some waistbands that are phosphorescence. Okay, when the light goes off, what happens? It still glows for some time. So that means the source will is has been removed, but it is still glowing. So it's a slow process. So you can see slow. That's for phosphorescence. But for fluorescence, like the dollar note, once you remove the source, you don't see it anymore. So it's a fast process. So this is the Jablonski diagram. So you should be able to draw this. Okay. Now the second part of the question said you should use it to explain the major difference between that. So all I need you to do is you can explain this if you wish, but you can also put it in a tabular form if you are asked a question like this. Okay, and what you have here is electronic transition. Here is S1 to S0. Here is T1 to S0. Okay, for phosphorescence. Then spin selection rule: spin allowed, spin forbidden. Typical lifetime nanoseconds. Phosphorescence can be milliseconds to seconds. It takes a longer time. Then emission persistent, stops immediately when excitation stops. That's fluorescence. For phosphorescence, continues after excitation ceases. That is for phosphorescence. So why is phosphorescence much slower than fluorescence? So these are the points: spin multiplicity change, low transition probability, metastable triple state, then dependence on spin orbit coupling. So this is just saying, you see, the phosphorescence goes through some extra steps, okay, before it returns back to the ground state. That is what you have there. Now we're about to end this. So we look at, in an experiment, 1 times 10 raised power minus 5 Einstein of light at 254 nanometers is absorbed, producing 5 times 10 raised power minus 6 moles of product. Calculate the quantum yield. This is a lovely thing for those that are doing SPF. So for my students that will be working on sunscreens, when we get there, we'll discuss. So for instance, when you buy sunscreen, you see SPF 50, SPF 30, some SPF 10 depending on how strong your sunscreen is. So it relates to this also, okay? So, but I wouldn't want to go into the theory as such, okay, except for those that might want to apply it. Now, the quantum yield is defined. You don't need to define the quantum yield for me, so this is not necessary. All I need you to do is just to give me the answer, the calculation and the answer, okay, which is what you have here, okay, what you have here. So for the quantum yield, we are looking at what is the amount produced over the amount absorbed. That is quantum yield. Okay, amount produced over amount absorbed. So, which is what you have here. 5 times 10 to the power minus 6 is produced. 1 times 10 to the power minus 5 is absorbed, right? And then you have 5. So when you buy a sunscreen, for instance, and it has a low this SPF, what it means is that uh, you know a lot of the light absorbed, because for SPF you actually want your SPF to be uh, a strong absorber, okay? So but and all of that, but that is for SPF anyway. I'll discuss that with my project students. But in this case, in the sense of fluorescence, okay, you can relate this to fluorescence. For fluorescence, you want your for like the dollar note, you want people to be able to see it once they put the light, to see the features. So in this case, the quantum yield should be very high, so that amount emitted should be far greater than amount absorbed, so that they can see the features on the dollar note. So that is why quantum yield is very important. Now to describe how chlorine radicals catalyze ozone destruction. There was a time this was a major issue. Many chemicals were banned, okay, from the market. Why? Because uh, when these chemicals are used, they destroy the ozone in the atmosphere, and that leads to direct sunlight. Sunlight hits the the surface of the earth directly, which is dangerous for the skin. It can cause skin cancer and all sorts of problems. So how many of them they contain chlorine radicals? So how do they destroy the ozone layer in the atmosphere? So when they rise, these are the steps you just need to give me. Okay. So Cl plus O3, ozone, that's O3 is ozone. So it gives ClO plus O2. So it breaks down the ozone to oxygen. Then again the Cl O plus O goes on to give Cl plus O2. So that is what you get. Okay, and then this is the net reaction. So everything, the ozone is converted to oxygen gas. So with this, you have answered this question. Last but not the least, state the Grotus-Draper law. The Grotus-Draper law simply states that only the light that is absorbed by a system can bring about a photochemical change. Only the light that is absorbed by a system can bring about a photochemical change. That is all. Okay. So if you wish, you can go ahead to explain. Okay. So that's that for this course. So if you have any question, please endeavor to post it in the comment section. So I'll be waiting for your comments.